like to introduce Jozuki Sato, who will be presenting GenAI powered network automation. Can LLM agents be network operators? Jozuki is an intermediate level network engineer at NTT Field Technologies. It's his first time presenting at NANOG, and it's a pleasure to have him here with us today. Welcome.
Now, let me begin my presentation. My name is Ryosuke Sato, and I work for NTT Field Techno Company that maintain infrastructure networks in Western Japan. This is my first time speaking at NANOG, and my English is not so very good, but I hope you will forgive me. Let's start. First, we'll explain the background and purpose of our initiatives. We have been working to automate network operations for a long time with the aim of reducing costs. Recently, with generative AI, that means large language models, LLM, we are exploring the expansion of our current network automation capabilities to address more advanced use cases, even the full delegation of operators' costs. Here are some examples of use cases we have implemented so far. But this case, limited to cases where the script can be written statically, such as Ansible playbooks or pure Python. As shown in figure below, for example, auto-healing for software of network devices. That is sorry. Existing use cases is limited to cases where scripts can be written statically. For example, auto-healing for software of network devices. If received for software, execute a reboot command. We have exhausted this type of automation and seeing little further cost reductions. But in cases like network troubleshooting, writing a static automation script proves challenging because it requires advanced autonomous decisions where subsequent actions are modified based on the outcomes of the investigation actions. Here's an example of a procedure for investigating the cause of the communication failures on some client terminals. First, searching their check traps, but nothing found. Next, checking communication with about ping. As a result, mission packet found. Finally, check the setting of the network equipments in the ping mission section. Finally, misconfiguration found. We would like to use LLM to achieve this, automate in this case such as this. We are continuing to experiment in order to achieve the kind of results in the previous cases. And we will introduce and share the technical challenges we encountered and our approaches to resolving them. First technical challenges is construction of multi-agent for network operations. Fine-tuning the single agents specifically for single task improves each accuracy, but advanced network automation cases requires multiple tasks. Therefore, multi-agent system that links multiple agents is required. This is the overview of multi-agent we constructed. It consists of 3 agents. First, orchestrate agents that's responsible for overall operation control. Second, network operation agents execute operations on network devices. Third, failure analysis agents that analyze the root cause of failures. These three agents work together to infer output based on input text. From that, I will explain the details of each agent. These are details of orchestral agents control the behavior of the entire agent, including actions to be performed, interpretation of results, and next actions. This is achieved using prompting techniques based on React, reasoning, and actions. Here's an example of prompt in orchestral agents. At the first of the prompts, instructs repeat reasoning and action step. So you as an excellent network operator, answer the following questions as best you can. You have access to the following agents and use the following format: question steps, source step, action input step, observation steps, and final answer steps. And so, inserting other information from network topology information, question as user input. Then, if this prompt run and outputs the agent, outputs the action steps, it means the calling agent, other agent. And in this way, orchestrator repeats the judgment process by adding the results of other agents to the prompt. This is details of network operation agents that interpret the instruction from the orchestrator and output in specific data formats for management interfaces on network devices. At this time, it's for JSON PC interface for Nokia and Linux. So instruction includes the output path parameter for JSON PC. And output format specifies output format paragraph as this. Output must be in list of JSON as the third it details of failure analysis agents that inference of root causes of network trouble. Additional information required for further analysis using information previously collected by other agents. So in information on network status paragraphs, inserting information by other agents. And the last of the prompts instruct analyze policy. Now let's move on to the second issue, that is inaccuracy of LLM output in the network operation domain. So because LLM lacks knowledge of network domain, especially vendor-specific implementations, the output will be inaccurate when performing automation. Then, this script, my example script to fetch interface status for Nokia and Linux network operation agents, but that output and incorrect path slash interface slash status. That's one output. There is no specification for JSON PC interface of Nokia and Linux. The approach to solving this problem is in-context learning. That improves the accuracy of the LLM reasoning by inserting specific information about the situation into the prompt. This information retrieves according to the situation using RAG or semantic search. This is an example of in-context learning for network operation agents. Little with the detailed JSON RPG interface specification from the documentation from the website of Nokia data references. And inserts to information as pinned paragraphs, the OS of the host of is Nokia SN Linux. Second, as a path information paragraph is the correct path the interface name and the operation state and adding description. That means interface statuses. We implemented the multi-agent system that reflects the approach described above. From here, I'll share you the results of evaluation of that agent in simple simulation networks. First, I'll explain network environment. That's simple. Cross-public configured with Nokia SR Linux using container that consists of 10 router nodes and 4 client nodes. This is a network traffic cases to be simulated. At this time, apply the filter settings to block only the communications protocol used by the user for communications. Accurate setting is inserted into spine nodes. As a result, some of the clients can't communicate, but there's no error, no traps. To investigate the root cause of this trouble is slightly difficult. Here's an example of how agent works for the simulation environment. First, input text from user. Some clients have reported that they are unable to communicate. Please investigate the cause and report it. First, orchestration run, and it shows the necessary performing ping test and output action steps to call network operation agents. So next agent to run is network operation agents. This agent executes tools for ping and output the results of tools. This is the part of it and the background. Ping from link for node to lift node, result success. It means. Retrieve the output from the network operation agents, orchestration agent run again. At this time, to further investigate the cause of failure, I'll use failure analysis tool agent. So next run is failure analysis agent. That it solves the issue. It localizes the path involving lift 2 and lift 4. That are ping missing sections. And requires an information. Interface statuses and accurate configurations of some nodes. Orchestration agents run again. And it's also necessary to gather information about the interface statuses and accurate configuration, as failure analysis agent says. And outputs action agents, action steps as they call network operation agents. And network operation agents execute the tools for retrieving interface and accurate settings. And print out this, including suspicious IPv4 filter. Entry action is dropped. The matching target protocol is HMP. This is a final run of orchestrator agents. it thought the analysis shows that the communication failures are primarily due to occur misconfigurations on spyware, which is blocking ICMP packets. So it's moved to final answer steps. The root cause is communication failure. It's due to occur misconfiguration on spyware, which are blocking to ICMP packets or successful communication between the nodes involved. So the ACL rules need to be modified to allow ICMP traffics. By performing this series of agent operations, we are able to troubleshoot the problem correctly as human network operator do so. We will move on to a summary and the presentation and the explanation of remaining issues. We have implemented a slightly complex network automation use cases using LLM multi-agents. And the confidence that it works as expected to a certain extent. But one of the issues that need to be resolved for further expansion is LLM inference strategy is as follows. The tendency is failure to follow negative instructions. LLM models almost tend to fail at negative commands, not to do, or must not do, and should not do. But many of the non-maintenance requirements in negative form when expressed in the straightforward manner, which poses a challenge in reflecting these requirements in the prompts. That concludes my presentation. Please feel free to ask any questions about the content. But I would appreciate it if you could stick slowly and use simple words concisely. Thank you very much for listening. Thank you.
Are there any questions in the room? Yes. Please go ahead. Make sure you state your name.
My name is Prabhakar. I'm with Sienna. Thank you for the presentation. So the LLM that you used for this example, was it hosted on-prem or it was in the cloud?
Sorry, please say.
The LLM, the large language model that you used for this example, where was it hosted? On-prem or on the cloud?
Is your LLM cloud-based or host-based?
Cloud-based. I use GPT-4 mini models.
Okay, thank you. And have you done any cost analysis, like how much money it costs for the ping example you showed, right? So
about 1,000 rounds, it is smaller for $10.
$10
for token costs.
And how much time it takes to troubleshoot?
About 3 to 5 minutes.
Okay.
And it was almost time of through executing on Python.
Okay. And last question. So this was the example where there was a misconfig in the network, but have you tried examples where configuration is good, control plane is good, but there is a problem in data plane?
So have you, in the example you have a misconfiguration, have you tried when your configuration is right, control plane is correct, but it's not working?
Yeah.
Did I get that right? Yeah. Your configuration is okay, and your control plane is okay. So like your routing table, everything is okay, but somehow your data plane is not working.
Yeah.
Yeah. Have you ever tried like that?
Yes, I tested the occur misconfigurations only, but other type of misconfiguration we now implemented to solve them.
Okay. Yeah. Thank you.
I guess that's next step.
Yes.
Yeah. We have a question online or any more question in the room? No? Okay. Thank you for your presentation.
Thank you.
Thank you for your attention.